Hi, my name is Yusuf. Today I will be presenting Project 2, Module 2 for class ECEN 4242 Communication Theory by Peter Mathis. So, the following diagram shows the super heterodyne transceiver, which uses a real bandpass filter. It is used in many applications, and I personally used it in designing Norcal 40A transceiver for wireless class. As it's shown, there are two sides for our transceiver. One is the digital circuit, which consists of the DSP, digital signal processing. The digital signal processing works with small frequencies. And the other side for our circuit is the analog circuit, which consists of bandpass filter, mixer oscillator, which shifts frequency, and low pass filter and power amplifier. The super heterodyne transceiver has a mixer oscillator that receives the signal from the antenna through the reception terminal and shifts it to an intermediate frequency where it's suitable for reception and transmission. For example, it shifts the signal to a low frequency for the DSP and shifts it back to high frequency to transmit it. So in this project, we are interested in transmission and reception of 802.11 type wireless local area network signal in the 2.4 GHz ISM frequency band. Such signals have a bandwidth of approximately 20 MHz, and the graph on the bottom shows the idealized spectrum of such signal occupying the range from 2400 to 2420 MHz. In this slide, I'm going to discuss how the signal in the previous slide is being transmitted. Starting from the DSP, the signal coming out of the DSP in figure 1 or in figure A, it will be real, centered at 20 MHz. Since we have the sampling rate to be 60 MSPS, that's been divided by 2, which gives us 30 MHz. So the farthest frequency that we could have in the frequency range is 30 MHz coming out from the DSP. And since the signal that's being produced by the DSP is real, it will have a negative component as is shown in the graph A that goes from -10 to -30. These two signals will go through the low-pass filter, and the low-pass filter will eliminate any other signal or any other noise signal in the system. Then it will send it through the mixer oscillator, which has a frequency of 4.21 GHz. In this case, these two signals will be shifted to the right by 4.21 GHz, and the resulted signal is shown at graph C. So, and there will also be an image signals that's reflected on the y-axis that's also shown in figure C. Then the signal will go through the bandpass filter. In this case, the bandpass filter will filter out all other signals and will keep the desired signal, which is from 2.4 to 2.42, and then it will send it through the transmitter to the antenna. The signal that's received at the receiving end of the antenna will be at 2.4 GHz. The signal will go through the low noise amplifier, and then it will go through the bandpass filter. The bandpass filter will filter out any other noise signal that's present in the spectrum, in the frequency spectrum, as it's shown in figure B. And then the signal will move through the mixer oscillator, which will shift the frequency back by 2.41 GHz to 20 MHz, to be centered at 20 MHz, as shown in figure C. So then this signal will have an image that resides at 4.81 GHz. So in order to get rid of this image frequency, we will set the signal through the low-pass filter, which in this case is going to eliminate the image frequency and take the wanted signal or the desired signal to the DSP, as it's shown in the last figure, which has only the frequency that's wanted. Inserting the parameters in the MATLAB, the response of bandpass cascaded filter is shown with an order of 16 on the right. I use the cascade because I want to minimize the amount of rippling when n is high as 16, and to get the cutoff frequency, which is 2.398 gigahertz. So as shown in the graph, that there is not big amount of rippling, and it's 2.398 at 40 dB. Another type of transceivers would be the direct conversion transceiver, which could be referred to as 0IF transceiver. It modulates and demodulates a signal through synchronous detection that uses two local oscillator and low-pass filters to shift frequency of the received or transmitted signal to suitable ranges of frequencies. It also uses the analysis of complex valued low-pass signal filtering. Therefore, the problem of image frequency has been eliminated. So here is a demonstration for the direct conversion transceiver. So we use two local oscillator in order to produce our signal to the DSP. To find these two signals going into the DSP, we first multiply the incoming signal x of t times the e to the negative j 2 by fct, which is cos 2 by fct minus j x of t sine 2 by fct, and all multiplied by x of t. Then we low pass filter it in order to get rid of the noise in the system and other signals that's undesired for the system. And we can see the equivalent circuit shown in the slide. For the transmitting of the direct conversion transceiver, the two signals will come out from the digital signal processing, and they will go through a local oscillator that shifts the frequency by cos 2 by fct for the xli, and by negative sine 2 by fct for the xlqt signal, and then it will add them up to bring out the final result, which is x of t, which is the recovered signal that has been demodulated in the direct conversion transceiver. In this slide, I'm going to discuss the suitability of real valued bandpass signal and complex valued low-pass signal. Since the real valued bandpass signal produces image frequency in the spectrum, that leads to a waste space in the frequency spectrum where the image frequency resides. It also leads for a waste of energy to create the image frequency itself, and a waste of energy to eliminate it. Whereas on the other hand, in the complex valued low-pass signal, there is no an image frequency that's been reduced. Instead, the complex valued low-pass signal uses the frequency shifting property in order to eliminate the need for the image frequency in the first place. So, in conclusion, complex valued low-pass signal is better since it's power efficient and provides more space for other signals to be accommodated in the frequency.